Hey y'all, and welcome back to Coding with Minmer. On today's agenda, we're going to tackle Leetcode problem 215, kth largest element in an array. After that, we'll go over two actual variants of the original question that Meta asks. Okay, let's get started. The problem description is well written, so let's just read it. We're given an integer array called nums and an integer k. As you can see in our example here, here's our list of numbers, as well as a k of 2. What we have to do is return the kth largest element in the array. Going back to our example, what is the second largest number? It's obvious that 10 stands as the first largest, making 3 the second largest. Therefore, 3 is our answer, and that's what we return. A quick note here, the problem description considers the largest element in the sorted order, not the kth distinct element. What's this mean? Let's look at another example. If we had these numbers and we wanted to find the sixth largest number, then we would count the two 3's as the first and second largest respectively. Yep, it doesn't matter if they're duplicates or not. The 3 2's would be considered the third, fourth, and fifth largest. That leaves us with the 1, which is the sixth largest. This is ultimately the answer, and that's what we return. Alright, so it's as clear as day what our goal is, but how do we solve this? If you take a peek at the LeetCode editorial, there are 4 solutions. Should you know them all by heart? I argue for the most part, no, it's not worth your time because there are hundreds of other LeetCode problems and variants to familiarize yourself with. Luckily for us, Meta only really expects one of the solutions so long as you justify your reasoning. I'm not going to go over the first 3 solutions, but I will point out each of their weaknesses, which is something you should communicate with your interviewer. Let's go through them one by one. First off, we have quick select. Although this is a big O(n) time complexity, it's also n squared in the worst case. And for example's sake, you can walk through this input right here to observe the exponential time complexity. You can really see it if you pick the rightmost element as the pivot for every iteration. Yes, this is a very contrived hypothetical, but you get my point. Moreover, quick select can be upwards 50 lines of code, so even if you're a fast typer, writing the entire algorithm within 15 minutes is a tough and error-prone task. Let's not opt for this solution. Second of all, we have count sort. This is generalized to big O(n) time complexity, where n is the maximum number found in the array. That's great and all, but if you have an example like this, 1, 2, 3, and then a 1 million, then you can really see the potential issue. You would have to make a vector of 1,000,001 elements and explode your space complexity to big O of 1,000,000 and iterate over a very large count array. That's also not ideal. Third and lastly, we can use an inbuilt sort algorithm for a n log n time complexity. This works just fine, but not only does LeetCode challenge us to solve it without inbuilt sorting, but if you suggest this route, Meta interviewers may also ask you this follow-up question. What happens if your given k is typically a very small number, like 1? Sure, the LeetCode constraints here specify that k is bounded by n, the number of elements we can be given, but Meta interviewers will go one step further to suggest that k will be way lower relative to n. They're hinting to you that you should use a minimum heap. Therefore, we're not going to opt for the n log n approach. A minimum heap will bring us to the fourth and ultimate solution that we will ultimately choose. Let's take a look. Okay, so the first thing we notice is that we have our minimum heap data structure already initialized here. How convenient. We also see that we're trying to find the second largest number in our given vector of integers. Furthermore, we observe that we have a k of 2 and an n of 5 of the 5 elements. So indeed, k is smaller relative to our n of 5. Before we start our walkthrough, I want to preface something and say, sorry, this is not a tutorial video on how heaps work under the hood, but all we need to know is that there are special properties of a heap that we can leverage to boost the performance of our algorithm. We'll discover these functions as we go through this example. What we'll do is iterate left to right through our vector of numbers and push each one into our minimum heap. On the first iteration, we have a 1. Therefore, we'll push it into our heap. This push function has a time complexity of log a, where a is the number of elements in our heap. We'll just take note of that here. Great, that's all we'll do on this iteration. Let's move on. On the next iteration, we have a for, so let's also push that. I'll make a quick note. Right now, the minimum heap appears as a black box data structure. It'll remain that way, and I'm okay with that. All we have to know is that whenever you push a value into a minimum heap, the values will be organized in descending order, where the bottommost element is the minimum element. Therefore, we have the for and then the 1. And while we're here, there's another neat function called top that, when invoked, will return the minimum number in our heap at any given time. It does this in big O1 time complexity. So on this iteration, maybe it's a coincidence, maybe it's not. We can call this function to actually get the kth largest number, the second largest number among all the elements we've seen so far. Here's a quick thought experiment. If our vector here hypothetically ended at the second element, and thus we only had the 2, then the 4 would be the first largest, leaving the 1 to be the second largest. This top function would return exactly that. Interesting. However, we can see that there are more elements to go over. Let's continue our loop. On the next iteration, we have a 3, so let's push it in log a time complexity, where again, a is the number of elements in our heap. Pushing the 3, we'll position it right here in descending order. Okay, let's pause real quick. Let's try the same thought experiment from the previous iteration. What if our vector ended right here and there was nothing left to add? Therefore, the 4 stands to be the first largest, and the number 3 would be the second largest, or in other words, the kth largest, and that would be our answer. We could try what we did in the iteration before and invoke the top function, but that still gives us the 1, not the 3. What gives? The issue is we have more than k elements in our heap. K is 2, but we have 3, 1, 2, 3. One of which is the current minimum number that is lower than our answer of 3 and thereby blocks it. This is what I propose we do. On any given iteration, after pushing an element, if our minimum heap ever exceeds k elements, like it does right here, then we should pop the minimum number, allowing us to now call the top function to return the running kth largest element. Right here, that's 3, and if you want to verify in our shortened vector, that is indeed the answer. Okay, let's make a couple notes. Popping, turns out, is also a log a time complexity function, but let's be a bit more specific. Since we only ever push or pop when there's roughly k elements in our heap, we can generalize the time complexity to be log k instead, where k is the same k we're given as input in the problem. Okay, that's actually all the logic. Let's continue on to the next iteration and consolidate all the ideas we've just put out there. On the next iteration, we have a 10. Let's push it in here. It's the largest by far, so our minimum heap will magically put it right here. The next thing we do is have an if statement. Is the size of our minimum heap larger than a k of 2? Yes, indeed, the 3 is greater than 2. What are we going to do? We're going to call the pop function with log k time complexity and remove the 3. And you'll note a pattern by now that popping will always pop the current minimum value in our min heap. This is a very convenient function for us because now if we were to call top and get 4, then 4 would indeed be the kth largest of all the elements we've seen so far. Let's go over this example one more time. So if 10 is the first largest, the 4 is indeed the second largest. That's great. Let's now move on to the last iteration, where we now have a 1. Let's push that into our min heap. It'll be positioned right here at the very bottom. That's our new minimum. We check our if statement. We have 3 elements. That's bigger than k of 2. Let's pop the minimum in log k. And just like that, we've finished looping through all of the elements. And just like on all the previous iterations, we called the top function to get the kth largest element. So that's what we'll do here. to return our answer of 4. 4, indeed, is the second largest number. That's our answer, and that's what we'll return. Okay, what is the time complexity? Well, we looped through all n elements, so that's for sure an n. But then on any given iteration, we might have pushed in log k, but also popped with log k. So to be exact, that's 2 times log k, which just boils down to a singular log k. Therefore, our overall runtime is n times log k. It may not seem like it, but n log k can be much faster than n log n if we were to use the inbuilt sort function. For example's sake, let's just say that n is 10 million and k is 10. If we plug those into this following equation, we would get an output of 10 million. But if we tried the same numbers with n log n, we would get 70 million. It's literally 7x. What a difference indeed. The space complexity is big OK because we only ever keep k elements in our heap at any given time. Here we have the 2 elements, and indeed, k is 2. Okay, awesome. Let's translate this into code. Okay, so the first thing we need is our minimum heap. It's named as a priority queue in C++. Don't at me, this is the syntax to initialize this data structure. It's a lot, I agree. Let's name it min heap to be consistent with our diagram. When that's ready for us, we can enter our while loop. We'll loop through each number, and on each iteration, we'll do 2 things. 1, we'll push the number into our minimum heap, and then move on to the if statement that if the size of the min heap ever exceeds k, then we'll pop the minimum number. This acts as a balancing act. Therefore, when we're done with the loop, we know for sure that min heap.top will give us the kth largest number. Okay, believe it or not, that is it. This problem is more tough conceptually than actual implementation. Fantastic. Let's take a look at the first variant. Okay, so this variant is just meant to confuse you because it introduces an off by 1 trick. Off by 1 errors are the bane of my existence, so let's be real careful as we walk through the problem. Alright, so we're given the same parameters. We're given an integer array called nums and an integer k. However, we now want to return the kth plus 1 largest number in the array. Let's check out our example. Here's our vector of integers and our k of 3. We no longer want to find the 3rd largest number, but rather the k plus 1 largest, or in other words, the 4th largest number. Looking at our vector here, the 9 is the 1st largest, the 8 is the 2nd, 6, 3, and finally the 5 as the 4th largest. That's the result, and that's what we'll return in our function. Okay, that seemed way trivial, and in many ways it is. All we would have to do in our existing implementation is to add the 1 to our k and go through the same logic with a minimum heap. That said, there is a dangerous edge case that may trip us up, and it stems from the fact that we add 1 to our k. Check out these constraints right here. Just like in the OG LeetCode problem, k is bounded by the number of elements we can be given, n, meaning the largest value k can take on is n. So what if in this variant we added 1 to k, thereby tipping it to exceed our n? Let's change our k in our example to 5, which means now we want to find the 6th largest number. But hold on, that exceeds the number of n elements we even have of the 5. 1, 2, 3, 4, 5. That's a problem. We see that 9 is again the 1st largest, the 8 is the 2nd largest, 6 the 3rd, the 5 the 4th largest, and the 3 the 5th largest. There is no 6th largest at all. Therefore, to remedy this, we'll just have an if statement at the very beginning of our function to check if k plus 1 is greater than n. If it is, we panic and throw an error. Other than these 2 changes, the if statement as well as adding 1 to our k, there's really nothing else to change about our algorithm. However, if you've gotten to this point, if your interviewer is evil, they'll tell you that you still have bugs or ask you whether your solution worked under different test cases. If this happens, try asking more clarifying questions about these constraints. For example, can k be negative? Or how about 0? Can we be given an empty vector? The list goes on. I'll leave these up to you. I'm not trying to make this an hour-long video and bore you, so I'll stop before we fall into too many rabbit holes. The time complexity and space complexity both remain the same from the previous solution. The time complexity is n times log k, and the space complexity is big O of k. Amazing. Like I said, none of the other code changes. Let's dive into the implementation. Okay, so like I said, there's only two things we have to do. Other than incrementing our k by 1, we have to be very careful where adding 1 to k makes it greater than n. So let's make that if statement that if k plus 1 is greater than the number of elements we're given n, let's throw an error. A out of range. Error does seem sensical to me. Let's leave a message for our users, k plus 1 cannot exceed n, good enough for me, and that's really it. Alright, let's head into the last variant. Meta does tend to stay true to the original LeetCode problem, but there's always a chance they ask you this variant. That what if now we wanted to find the kth smallest element in the array? All the other requirements remain the same, so the problem is basically asking for the opposite solution of the OG problem. And if that's the case, we can imagine its opposite day so that instead of a minimum heap solution, we'd rather trash that and opt for a max heap. Thankfully, we don't have to reverse any other logic. The other bits of our code from before will still work excellently. With this idea, let's go over an example. As you can see, here's our nums of integers, and we have a k of 3, which means we now want to find the third smallest element. Taking a look, this 1 is obviously the first smallest element, the 3 then would be the second smallest, and the 5 the third smallest, and thus is the resulting integer that we return. That said, we are coders. Let's approach this in a programmatic way that, other than a change in data structure, will be the same exact way we'd gone through the OG LeetCode problem. Let's initialize our max heap data structure, where the values are now organized from the smallest to the maximum number. It's just the opposite from before. And similarly to the OG problem, we'll loop left to right and push each number into our max heap. And we'll do some popping if the size of our heap ever exceeds our k of 3. This way, remember, we can always call the top function to access the kth smallest element. Okay, let's go. On the first iteration, we have a 7. Let's push it into our max heap. It'll go right here. The next thing we'll do is see if the size of our max heap is greater than a k of 3. No, 1 is not bigger than 3, so we'll move on. On the next iteration, we have a 3. Let's push it into our max heap. It's going to go before the 7 because of the ordered guarantee that a max heap gives us. Do we have more than 3 elements? No, we don't, so we move on. We now have a value of 8. If we push that into our max heap, it's going to go right here. We haven't exceeded 3 elements yet, but we will when we iterate to the next iteration where we have a 5 and insert it, making our max heap have one too many elements, a size of 4, is greater than our k of 3. So we'll call the pop function, thereby removing the current maximum number in our heap, thus revealing the third smallest element so far. And just like before, we can prove this too. If we're saying that these elements are all the elements we've seen so far, because that's currently where we've iterated up to, then the 3 is the first smallest, 5 is the second smallest, and 7 is the third smallest. So yes, it is true, our top function would return this very answer. Amazing, we rest easy and continue our loop knowing that our algorithm will work. On the next iteration, we have a 10. If we push that into our max heap, it will be the new maximum. But just like the previous iteration, we have one too many elements. Let's pop the current maximum. It just so happens to be this 10. It had a short life. Let's delete it and move on to the last iteration where we have a 1. Inserting that, we'll position it right here. Once again, we have the same issue. We have 4 elements that's greater than the 3. Let's remove the current maximum of the 7, and we're done looping through our vector. The very last thing we'll do is get our answer. How do we do that? Just like I showed before, we'll call the top function, which will return for us the kth smallest element. It's the 5, and that's the algorithm. The time complexity is n times log k. It's not changed, and neither has the space complexity. It's still big OK. Great, let's code this up. Okay, so take a look at the method signature. We're indeed trying to find the kth smallest, no longer the kth largest. Therefore, we'll opt for a max heap, which thankfully for us, is a simple declaration. Let's rename our heap to max heap, that makes more sense, and rename it wherever it's referenced. And with that said, that's all the changes we have to make. That is it. Good luck on your interviews. And if you learned something today, please make sure you like, comment, and subscribe. Thanks for watching.